Hi, and welcome to Unit 10 Mini Lecture 1 for Astronomy and Astrophysics for Educators. In this lecture, we're going to talk about our own galaxy, the Milky Way.
So if you go somewhere on the surface of the Earth where there isn't much light pollution and look up, you will see a band of stars arcing across the sky. The Greeks called it the Milky Circle. The Romans called it something similar, the Milky Road or Milky Way. So what is it that we're looking at? Well, by the mid-18th century, astronomers knew that this band of light was actually the light from an enormous number of distant stars. The first attempt to map out the distribution of stars and try and put together a picture of what the overall system of stars in which we're embedded looks like were William and Caroline Herschel in 1785. They published their so-called grindstone model, the Sun placed at the center of an irregularly shaped disk of stars. This is a side-on cross-section through that disk. It was named the grindstone model because it resembled a very irregular version of a flat disk, like a grindstone. The Sun is roughly at the center, as I mentioned. The Sun was placed roughly at the center. The next step in constructing the model, the next step forward, was the realization that the Sun was actually not at the center of whatever this collection of stars was. In 1922, Jacobus Kapteyn's model placed the Sun some way outside the center of an ellipsoidal distribution of stars that were about 17 kiloparsecs in diameter and about 3 kiloparsecs high. We're now moving much closer towards what the actual distribution of stars looks like. The next key breakthrough came with Harlow Shapley, who noticed that although open clusters were randomly scattered about the sky, globular clusters were concentrated in the direction of the constellation of Sagittarius. So reminder, a globular cluster is a collection of millions of stars arranged in a roughly spherical cloud. And he was able to plot the positions of the globular clusters on the sky. This is a map of the positions of all of the globular clusters, and they're concentrated in one spot on the sky. What he hypothesized was that the spot where they were concentrated was the direction towards the center of this overall system of stars that we are inside of. So this assumption is based on the hypothesis that globular clusters will be concentrated towards the center of the collection of stars that we're a part of. This is a map of the actual distribution of globular clusters throughout the Milky Way, and this shows the location of our Sun in the position we know it is today, some way outside the galactic center, about 8 kiloparsecs to be precise. So if we look in the direction towards the galactic center, we see far more globular clusters than if we look in any other direction. A final step to getting the true scale and size of the Milky Way came in realizing that starlight was being dimmed by passing through the interstellar medium. Previously, astronomers underestimated the size of the galaxy because they took the brightness of the stars that they saw to be their true brightness rather than the brightness dimmed by the intervening matter. So this is the basic picture of the Milky Way that we have built up by observations today. So the Milky Way is a galaxy that is made up of a disk, which is a thin circular shaped collection of stars with a central bulge. The Sun is located about 8 kiloparsecs out from the galactic nucleus, the center of the galaxy. And then there are all these globular clusters, which are smaller collections of stars that are distributed in a roughly spherically symmetric pattern that we call the halo of the galaxy. The galaxy itself, in terms of visible matter, is about 50 kiloparsecs in diameter. If we were able to look down on our galaxy from above, we would notice even more structure. The disk of the galaxy is actually contains spiral arm structures. These spiral patterns that are made up of regions where there is a lot more star formation and therefore a lot more newer, brighter stars. There's also a lot of gas, especially hydrogen, in the spiral arms. Here's the bulge of the galaxy, the central bulge, and the nucleus. Here's the sun, sandwiched in between the two major spiral arms, the Scutum Centaurus arm and the Perseus arm. There are also a series of smaller arms, spiral arms, the Sagittarius arm. We're near the Orion spur, which is sort of a continuation of that. Okay, so let's run down some basic facts about our galaxy. The disk of the galaxy that contains the spiral arms, that's where the most stars and dust are contained in our galaxy. It contains most of the giant molecular clouds, so this is where all the star formation takes place. It contains all of the open clusters, which are between a few million to a billion years old. Those are clusters such as the Pleiades and the Hyades. Now, if you actually made a scale model of this, the disk itself is thinner than a thin pizza crust compared to its diameter, just to give you a sense of scale. The diameter is 50 kiloparsecs, which is around about 150,000 light years. The halo contains about 200 globular clusters at an average age of about 11 billion years. So these are much, much older stars in general than the disk stars. The spiral arms are long spiral patterns of bright stars, H2 regions, star clusters, gas and dust. Our sun is located on the inner edge of the Perseus arm in the region called the Orion spur. The galaxy is rotating in that the stars are all orbiting the galactic nucleus. Our solar system takes about 225 to 250 million years to orbit the galactic center. So disk stars are much younger than halo stars, and there are several other important differences between stars in the disk and stars in the halo. As this picture shows here, disk stars are on roughly circular orbits around the galactic center, whereas halo stars tend to be on much more elliptical orbits that are inclined to at an angle to the galactic disk, and that tend to precess in that angle. Now, just a reminder, astronomers define metals to be any elements that are not hydrogen or helium. We can divide stars up into a number of populations. Population 1 stars are metal rich. That means 2 to 3% of their mass is in metals. Population 2 stars are metal poor. They have typically 0.1% of their mass made up as metals. Population 1 stars are located in the disk and population 2 stars in the halo. What that tells us is that population 1 stars, which are metal rich, these are made up of material that has been through the process of stellar birth and stellar death a number of times. Every time a material passes through the life cycle of a star, the number of heavier elements, the number of metals, increases because that is where metals come from. They are manufactured inside of stars. Population 2 stars, being metal poor, they are stars that are very, very old, stars that have been around since not long after the very first stars in the universe. So they're long-lived stars, and they haven't had a chance for their material to be recycled several times and therefore increase the proportion of metals in them. So how do we know that our galaxy has spiral arms? We haven't sent any probes outside of the galaxy. That would take millions of years. So we haven't been able to photograph our galaxy from the outside. So we've had to figure all of this out by studying the structure from within. And key to this is the 21 centimeter radiation we introduced a few weeks ago. This is radiation that is emitted by neutral hydrogen gas when the electron in the hydrogen atom flips its spin. Now, the spiral arms contain a lot of hydrogen gas. So let's say this is our sun, the galactic center is this way, and we are orbiting in a roughly circular orbit. The spiral arms aren't circular. So as we move in our orbit, we will actually have a relative velocity that carries us towards the outer spiral arms and away from the inner spiral arms. So that means that 21 centimeter radiation in the outer spiral arms that we detect will be blue shifted. They will be moved to higher frequency. When we look at the signal that we get from galactic 21 centimeter radiation, we see something like this. 1420 megahertz is the frequency corresponding to radiation with a wavelength of 21 centimeters. We detect one signal at slightly higher frequency than that, and another larger signal at a higher frequency, still close to 21 centimeter radiation, and still with a shape that is recognizably identifiable as that from 21 centimeter radiation. So this tells us that there is a band of material out here that forms this first spike and another band that forms the second spike. By doing more in-depth analysis, one can piece together the structure. So this is what you see along this line of sight. If we change our line of sight, then these will shift again, and you can piece together the shape of these bands of 21 centimeter radiation, and we find, lo and behold, they are spiral shaped. Okay, what is the mass of the Milky Way? How do we figure that out? Well, one way you might think of doing it is to use Kepler's third law. Okay, the planets in our solar system, as we've seen early on in this class, form a straight line when you plot on a logarithmic plot their period versus the distance from the sun. That's because periods squared is proportional to the distance from the sun cubed. That's Kepler's third law. The constant of proportionality gives you the mass of the sun. So if we were able to measure the orbits of stars around the center of the galaxy, that would tell us something about the mass of the galaxy as a whole, because these individual stars are orbiting because of the gravitational field of the galaxy as a whole. Now, another way of plotting this is to plot a rotation curve. So instead of period versus distance, you plot speed versus distance. You just convert period into speed by dividing the circumference of an orbit by the period. And this is the characteristic Keplerian rotation curve. Now, all of the planets are outside of the sun, but the stars in the galaxy are within the galaxy. So we would only expect to see a curve of this shape when we plot the speeds versus the distance to the center of the galaxy for the stars that were the furthest out from the center of the galaxy, because then most of the mass of the galaxy is inside of them. Well, you can do that. You can measure the speeds of stars and plot that speed versus the distance from the galactic center, and this pink line here is the shape of the rotation curve that you get. Now, by the time you've got out to about 15 kiloparsecs, 99% of the material of the galaxy is inside of you, and you would expect this curve to begin to form Keplerian motion. But you do not see that. Now, I'll come back to that point in a minute. Nevertheless, at this point here, you can still use this curve to figure out how much mass is inside a radius of about 15 kiloparsecs. And what you find is that the mass of the galaxy is about 400 billion times the mass of the sun. If you think that the average mass of a star is probably a few solar masses, then this tells you that there's about 100 billion stars in our galaxy. Okay, so why does the measured rotation curve not match the Keplerian rotation curve? Okay, this is what we would expect. This is what the stars should do. This is the rotation speed they should have if out here most of the mass of the galaxy is inside of their own orbital radius, which is what it appears to be observationally when we just look at the stars. Beyond about 15 to 20 kiloparsecs out from the galactic center, we don't see any matter. We don't see stars. We don't see gas. We can't see light from anything, and we can't see anything indirectly. But that's not what is happening. Instead, the stars are still orbiting essentially too fast. The stars out at the edge of the galaxy are orbiting too fast. The gas that is out there is orbiting too fast. Too fast if the matter that we see and can detect is the only stuff there is. When you do the calculation, in order to match the observed rotation curve, we require about 10 times more matter in our galaxy than the matter that we see, and we require it to extend out to much greater radii than the matter that we see. So there is 90% of the mass of the galaxy that we're just not seeing. The vast majority of it cannot interact with light. It cannot be emitting or absorbing light, or we would detect it. And since it doesn't interact with light, astronomers have named this stuff dark matter. We'll come back to dark matter in the final 2 weeks of this class. Finally, let's take a quick look at the center of the Milky Way. So if you take a very long exposure photograph of the Milky Way in the night sky and zoom in the direction of Sagittarius, then what you see is a patch of sky that is very bright in X-rays. And if you zoom in on the brightest spot, you find a region of space that we call Sagittarius A star. This is a region of space that releases a huge amount of X-ray radiation, and it appears to be located at the very center of our galaxy. If we zoom in even further, Sagittarius A star, where most of the X-rays are coming from, is seen here. If you zoom in on this region of sky, then the central point where a lot of these X-rays are coming from, Sagittarius A star, we can't actually see anything there. There is no star or anything there. There are a bunch of stars around it, and they're all orbiting on very elliptical orbits. Now we can measure the size of their orbits and their periods, and they are orbiting very quickly. And you can use, again, Kepler's law, the laws of Newtonian physics, to figure out what the mass of whatever it is that is located at the very center of our galaxy has to be. The result you get is that it must be around 4 million solar masses. So there must be an object here that weighs 4 million times the mass of our sun. We can see the size of the object, so we know how small the object must be. It must be inside a radius of 120 astronomical units. Actually, more recent observations place it inside 40 astronomical units. So that's just the size of our solar system. So there must be an object which is about the size of our solar system, but whereas our solar system has one solar mass contained within it, roughly, this has to have 4 million solar masses. The only way you can fit that amount of matter inside such a small region of space is if that mass is in the form of a black hole. So there is strong evidence that there is a giant so-called supermassive black hole at the center of our galaxy. Here is an animation of the observed orbits of the stars around the center of our galaxy. These are all stars that we can observe directly, and their orbits around the center of the galaxy, that close to the center of the galaxy, are so quick that we can track them in real time. So this is over a period of time from 1995 through to 2010. And we can track and calculate the orbital periods of all these stars and confirm that indeed at this point here you must have several millions solar masses worth of material. Here is another chart showing the list of stars and their positions at various time intervals. I will post this video as well, which is another nice illustration of the orbits of the stars at the center of the galaxy in this week's material.